Fractions and decimals. Speaking of simplification, our next subject is anything but, especially on the GRE. For whatever reason, GRE writers seem to love making you work with fractions. You'll have to compare them, simplify them, add them, multiply them, and divide them. You'll even have to convert them to decimals, and convert decimals to fractions. Did we mention that GRE writers love fractions? While talking about exponents earlier, we mentioned that a fraction has two parts: the numerator, the number on top, and the denominator, the number on the bottom. It's old vocabulary, we know. It never hurts to have a review, no matter how old the material. When working with fractions on the GRE, there's one key point you'll want to remember. Always reduce your answer completely. If you don't, it's unlikely you'll see your answer in the list of choices. Thankfully, reducing fractions isn't exactly rocket science. 4/8 can be reduced to 1/2, 3/9 to 1/3, 26/54 to 13/27. Reducing fractions should be old hat, but just in case, reduce fractions by common factors. Make them as small as possible while still remaining factors of the original numbers. Easy enough, right? Now, let's complicate it. Let's do some arithmetic with fractions. Usually in math, we think of addition and subtraction as easier than multiplication and division. After all, in elementary school, we learn addition and subtraction first. But in the wonderful world of fractions, multiplication and division tend to be easier. So we'll start there. To multiply fractions, just multiply straight across. Multiply numerators together, and then multiply the denominators together. We'll do a quick one. Multiply 3/8 by 2/3. 3 times 2 is 6. 8 times 3 is 24. The new fraction then is 6/24. Now reduce. 6 actually divides into 24, so our final fraction is 1/4. Pretty painless, right? Dividing fractions isn't bad either. We start by flipping the second fraction in the expression so the denominator is on top of the numerator. The flip number is called the reciprocal, which is just a fancy way of describing a number's inverse. So 3/4 is the reciprocal of 4/3, and the reciprocal of 1/5 is 5. Once we've got the second fraction's reciprocal, we just multiply. Another quick example. 3/5 divided by 1/2. Flip 1/2 to 2/1. Now multiply. 3 times 2 is 6. 5 times 1 is, of course, 5. Our new fraction is 6/5. More likely than not, knowing the GRE, you'll have to change that 6/5 to a mixed fraction, the integer fraction combo. This one is pretty easy. You know that you can take 1 right out of that fraction. The easiest way to do that is called 1 5/5. Since in math, 1 can be whatever you want it to be, so long as it's actually 1. What's left is 1/5. So your answer would be 1 1/5. Hang on to that rule about the number 1. It's a helpful trick anytime you're working with mixed fractions. Not bad, right? How about a little practice? The best place is with quantitative comparison because fractions can be a little misleading when it comes to quantity. So, in a quantitative comparison questions column A, we have 4/7. In the column B, we have 3/19. So which is bigger? This can be done quickly with some multiplication. Some cross-multiplication, actually. Put the two fractions side by side. To compare them, we just multiply diagonally up from each denominator. So we multiply the numerator of one fraction times the denominator of the other fraction, and then do the same with the other numerator and denominator. Since our fractions are 4/7 and 3/19, we multiply 4 times 19 and 7 times 3. That gives us 76 and 21. We can write 76 right beside 4/7 since that's the number we got by multiplying the numerator of 4/7. And we can stick 21 next to 3/19 since we got 21 when multiplying the numerator of 3/19. Since 76 is bigger than 21 and it was produced with the help of the numerator in 4/7, 4/7 is the bigger fraction. 4/7 is in column A. So we'll pick choice A, which in quantitative comparison questions always tells us that column A is bigger. You may in grade school have heard this cross-multiplication technique as the bow tie method. If you're not a huge fan of attire-based mathematic operations, cross-multiplication will do just fine. The bow tie isn't only for comparing fractions, though. It's also handy for adding and subtracting fractions with different denominators. The type of fractions that just happen to be the only kind you'll be asked to work with on the GRE. When you need to add or subtract fractions with different denominators, you'll have to convert the fractions so they have the same denominators. To convert fractions, we use a refined version of the bow tie technique. Multiply the denominators of the two fractions to get a new denominator. Then, do your cross multiplication up from each denominator like we did earlier. The numbers we get from cross-multiplying become our new numerators. Now, we can add or subtract the two fractions by just adding or subtracting new numerators and putting them on top of the new denominator. Try this out on your own while working practice problems. This is an excellent time to segue into the fraction's close cousin, the decimal. GRE writers love decimals almost as much as they love fractions. The best way to handle complicated decimals is to pretend like the decimal point doesn't exist at all. Multiply or divide to your heart's content, then stick in the decimal point at the end. Let's try a quick multiplication example. 3.456 times 2.13. Erase the decimal from your mind and instead multiply 3,456 by 213. Once we have our product, 736,128, we can figure out where the decimal goes. Look at the original problem and count the total number of digits that came after the decimal point. In this problem, there are a total of 5 numbers after the decimal point. Just shift that over to the product. So, 7.36128. Dividing decimals isn't much harder. Rewrite the problem as a fraction, and then move the decimal point all the way to the right. Just be sure to move the decimal point in the other number to the right the same number of spaces. Here's an example. Let's say we're asked to divide 0.76 into 23. Rewrite that as 23 over 0.76. Then rewrite the denominator as 76. Since we moved the decimal 2 spaces to the right in the denominator, we need to do the same thing to the numerator. 23 now becomes 2300. Your new problem is 2300 over 76. Much easier to digest, right? Unfortunately, with GRE math, there's more to decimals than the 4 standard operations. Sometimes, questions give you information in a decimal and expect an answer in a fraction, or they might give you information in a fraction and want an answer in a decimal. Decimals to fractions, even complicated ones, can be easily figured out by simply reading the decimal correctly. For instance, 0.389 is 389 thousandths. Just hearing that instructs you to write the fraction 389 over 1,000. Going in the other direction, from fraction to decimal, should be pretty easy as well. Here's a quick one. Convert 5/7 to a fraction. Do some old-fashioned long division to see how many times 7 goes into 5. If you worked it out on paper, you'd come up with 0.7142 and then some more numbers after that. But the GRE won't ask you for a decimal longer than 4 digits, so you can call it an answer at 0.7142. Many moons ago, you learned about permutations in math class and then promptly forgot about them, mostly because you couldn't possibly find a reasonable use for permutations. Well, here's that use, taking and passing the GRE. Let's do a real quick refresher on permutations. A permutation is an arrangement of things in a definite order. We use permutations to figure out how many different ways we could, say, organize some books in a box or listen to the 120 songs on your iPod shuffle. It's hard to miss permutations. They're the only math questions involving exclamation marks. Not that those exclamation marks are signs of excitement. They're factorial signs, and they are always on the right side of the number whose permutations we seek. An example, perhaps? Say you're asked how many different ways you could organize 5 books. You'd see the number 5 followed by an exclamation mark. To find the number of possible permutations of these 5 books, we just multiply 5 times 4 times 3 times 2 times 1, which gives us 120. This just means that there are 120 different possible ways, or 120 permutations, of how we could organize those books. Likewise, if you were figuring out how many possible ways you could listen to the 120 songs on your iPod shuffle, you'd multiply 120 times 119 times 118 times 117. Well, you get the idea. You'd multiply starting with the factorial number followed by every consecutive smaller positive integer after that. Luckily, the GRE won't give you any factorial problems involving gigantic numbers. Otherwise, you might spend 45 minutes on a single problem. Algebra. So far, most of our work has been with integers and strict numbers. That's basic arithmetic. Now it's time to move on to the more abstract. The x's, y's, z's, n's, and b's. Algebraic variables, in other words. We've talked a little about solving for variables. As we showed you earlier in the quantitative comparison examples, plugging in numbers when you've got multiple variables can be a great way to solve time and answer tricky algebra problems. Sometimes, you'll just have to deal with one variable. When this happens, you just need to get all of the numbers on one side and the variable on the other so that the variable equals the number. If you have to add, subtract, or divide to isolate the variables, just remember that anything you do to one side of the equation, you must also do to the other side. Otherwise, you'll probably find the wrong answer. In a minute, we'll look at some of the more complex ways you might work with variables on the GRE. But before we do, we should warn you. We'll help you brush up on some key formulas and share some tips for solving problems, but there are some things you've got to do yourself to really get. Averages. You all know about averages. In high school and college, you probably worked out a couple of class averages. By the way, just a little off-topic tip, that's not really going to work in grad school, where there's only two possible grades, pass and fail. We have to get you to grad school first, of course, so let's get back to the test. Specifically, let's talk about GRE vocabulary. For instance, sometimes the GRE calls averages means. You'll remember that a mean is just a way of referring to the total value of all the numbers in a set divided by the total number of numbers in that set. By set, we just mean a group of things. That's another term you'll probably want to memorize. If we gave you a bunch of numbers and asked you to find their average, we're fairly confident you'd know what to do. The GRE writers also know you can do this. So instead, you'll be tested on averages using variables. Crafty, right? You'll get average questions that tell you an average and ask you to find a number in the set you were averaging. It'll probably sound something like this. Jill's average for 4 English tests was 85 out of a possible 100. If her scores on 2 of the tests were 80 and 92, what is the lowest that either of her other 2 scores could have been? To solve this problem, we need to start by writing our own equation, where 85, Jill's average, is set to equal t over 4. Here, t is the total of all Jill's test scores, and 4 is the total number of tests she took. We can then solve for t by multiplying both sides by 4, so t equals 340. Now that we know this, we can create an equation where 340 equals 80 plus 92, the 2 scores we do know, plus x plus y. X and y are the unknown scores. Since we need to separate the variables and raw numbers, we subtract 80 and 92 from both sides, which gives us x plus y equals 168. The temptation here is to use substitution and plug in different combinations of numbers that add up to 168. That would probably take too much time. Remember, the highest score Jill could have gotten is a 100, and 100 plus what gives us 168? 68, obviously. Could Jill have gotten a lower score than 68? Let's see what happens if we subtract 99 from 168. We get 69. And if we subtract 98, we get 70. The numbers just get higher from there. So the lowest score she could have gotten is a 68. That doesn't mean she definitely got a 68, but it's the lowest possible score, which is what the question asks for. Before we move further into the land of algebraic unknowns, we should remind you of 3 other key math terms related to average or mean. First is standard deviation. The GRE won't ask you to calculate standard deviation, but if you see a reference to it, you should know that the term refers to how much the numbers in a set vary from the mean. Here's a good rule of thumb to remember about standard deviation. The bigger the standard deviation, the more widely dispersed the values are. And the smaller the standard deviation, the closer the values in a set are to the mean. So the standard deviation of the numbers 25 and 35 is bigger than the standard deviation of 4, 5, and 6 because 25 and 35 are more widely spread out than 4, 5, and 6. Now that we've got that down, do you remember what the median and mode are? That's right, the easy averages. Median being the number that's exactly in the middle of a set, and mode being the number that appears the most in a set. Simultaneous equations. Sometimes, the GRE will ask you to solve for more than one variable. Maybe you'll be asked to solve for x plus y, or a plus b, whatever the GRE writer's variable combinations du jour happens to be. To figure out these kinds of problems, the GRE will give you 2 equations that include both of those variables. For instance, you might get a question like 5a plus 4b equals 6, and 4a plus 3b equals 5. What does a plus b equal? At first glance, these kinds of questions can seem a little terrifying. Are you supposed to reduce them? Divide them? Multiply them? Wave your white flag and surrender? Actually, you just need to add or subtract these 2 equations from each other. Unfortunately, it's your job to know that. You heard the way that question was phrased. The GRE will not say, add these two equations to figure out what a plus b equals. That's where your brains come in. Well, and us too, of course. These are called simultaneous equations because, well, you're working with two equations simultaneously to figure out the sum of their variables. When you encounter a simultaneous equation problem, you just need to add or subtract the two equations so you end up with the sum of the two variables. Unfortunately, you won't get any clue as to whether you need to add or subtract the two equations. So let's look at the two equations in the question we introduced a few moments ago. 5a plus 4b equals 6, and 4a plus 3b equals 5. To figure out what a plus b equals, we need to start by stacking the two equations on top of one another so the a's and b's line up. The equal signs and plus signs should be lined up on top of each other too. Once we write this out as 5a plus 4b equals 6 on top of 4a plus 3b equals 5, we notice that 5a is right on top of 4a. If we were to add 5a and 4a, we would end up with 9a. But that'll just give us a bigger number, not help us simplify. So we probably don't want to add the equations. With subtraction, it looks like we'll gain a little more traction. 5a minus 4a obviously is just a. Talk about simple. So let's run subtraction through the whole problem. If we subtract 4a plus 3b equals 5 from 5a plus 4b equals 6, we'll end up with a plus b equals 1. And that is exactly what we're looking for. Sometimes, though, you won't be quite so lucky and will find yourself simplifying things a bit further. Simultaneous equations are one of those things that can rock your world if you just listen to us work problems. Be sure to work simultaneous equations on your own for practice. Inequalities. The real world is full of inequalities, and GRE math is no different. Throughout the math section, you'll see the inequality symbols for greater than or equal to, less than, and less than or equal to. You recognize them as the funny left and right pointing V-shaped signs. Your grade school math teacher may have referred to them as alligator mouths or pointing fingers. Silly as it seems, we like the alligator analogy, particularly since we can't show you the symbols. So here's a quick gator refresher. The number or variable that the alligator opens his mouth towards is bigger. The number or variable the alligator seems to be pointing at is the smaller one. And when the alligator mouth has a line underneath it, that means or equal to. So if the alligator has its mouth open toward one number and there's a line under the mouth, that number or variable is greater than or equal to the other number or variable. When you get a problem on the GRE involving an inequality sign, it'll look just like an equation without the equal sign. Usually, you can work with inequalities just like you work with equations. The one exception is if you have to divide both sides by a negative number to simplify the problem and solve for the variable. When this happens, you have to reverse the inequality sign. So if the alligator mouth was pointing left originally, it'll point right in your answer. Many people forget this, so GRE writers love to use inequalities involving negatives, just to see if they can trip you up. Since inequalities are one of those things that you have to see to really get, it's up to you to practice working with them in more depth. Just for good measure, though, we'll go on and do one together. Take the following problem. 14 minus 7x is less than 3. What is the approximate value of x? The question uses the word approximate because, of course, we can't figure out exactly what x equals, but we can determine whether it's greater than or less than another number. To do that, we first need to get 14 on the other side of the less than side to isolate our variable. So we'll subtract 14 from both sides. That means our inequality is now negative 7x is less than negative 11. To isolate x, we need to divide both sides by negative 7. And since 7 is negative, we've got to flip that inequality sign. So we end up with x is greater than 11 over 7. If we want to simplify that into a mixed fraction, we can write it as x is greater than 1 4/7. As long as you work equations with variables, inequalities are easy. Just remember to flip the sign if and only if you divide both sides by a negative number. And if you don't have to divide both sides by a negative number, leave the sign just like you found it, pointing and making fun of some poor little number. A lot of the time, you'll see inequalities with a vertical line on either side of some of the numbers or variables in the problem. When you see these vertical lines, the question is fishing for an absolute value. The absolute value symbols are just asking you to give the number without regard to its sign. So, if the number inside the absolute value sign is -3, the absolute value of that number is 3. This means both 3 and -3 have the same absolute value of 3. Functions. Alligator mouths, finger pointing, algebra and the GRE are all about the crazy symbols, aren't they? Believe it or not, that's just the tip of the iceberg. You know the @ sign, the number sign, and the ohm, that horseshoe-looking symbol? They are also symbols on the GRE. To top it all off, they're not even real mathematical symbols either. The GRE uses the @ number and horseshoe signs in functions. Don't break a sweat now. These aren't those real mathematical functions that you learned about in calculus. No f of x equals. GRE functions are an invention unto themselves, and they would scare the heck out of you if you didn't study for the test. Luckily, you won't have that problem. Here's a typical GRE function question for you. X at y is equal to x minus y over y plus 3. What's the value of 3 at 2? Sounds tricky, but it's just about the simplest substitution question you could imagine. This question is just asking you to substitute 3 for x and 2 for y. The @ sign is there just to throw you off. If there were a number sign or a horseshoe in place of the @ sign, it'd be asking you to do the exact same thing. So when you see a functions question, just substitute and do as told. These are softball questions. Run with them, not from them. Percentages. Another number you'll see a lot of on the GRE is the % sign. Most of the questions about percentages will be data interpretation problems. These are exceptions, and sometimes you'll find them in the problem-solving and quantitative comparison questions. You'll almost certainly be required to convert from a percentage to a decimal or fraction. As you probably remember, the word percent just means divide by 100. So if you see a 23 with a percentage sign after it, you're also looking at the fraction 23 over 100 and the decimal 0.23 or 23 hundredths. You'll also find yourself looking for the percentages of various integers. Here's an example. 3 is what % of 15? To figure out the answer, just translate the question into an equation. When you do that, remember that the word is in the question just means equals, and the word what is an unknown quantity, so it should be a variable. We'll use x. Our resulting equation then is 3 equals x% of 15. Then we just have to figure out the value of x. And since we know percent means divided by 100, we can rewrite x% as x over 100. Now we just need to do the math. First, multiply 15 times x, which gives us 15x over 100 equals 3. So to solve for x, we need to isolate this pesky little variable. Multiply diagonally up from 100 times 3 and diagonally up from the invisible 1 underneath 3 up to 15x. That gives us 300 on one side of the equation and 15x on the other. Then, since we're trying to get rid of that 15 next to x, we can divide both sides by 15 to solve for x. So what's 300 divided by 15? It's 20, which means 3 is 20% of 15. Just keep in mind that the writers will do all they can to word these problems as tricky as possible. So instead of 3 is what % of 15, you might get something like, what % of 15 is 3? Or even, what % of 3 is 15? Which is sort of the same problem, but in reverse. Just read everything carefully. And of course, do plenty of practice problems. Frequently, the GRE asks questions involving increases and decreases in percentages. One way they'll do this is by giving you a value, offering up some percentage increases or decreases, and then asking you to find the number that reflects the change in value. Here's an example. If the price of $3 a gallon gas increases by 25%, what is the new price of gas? To solve this type of question, you just have to figure out what 25% of 3 is and add that to $3. It seems pretty easy, but many GRE test takers read a question like this, figure out what 25% of 3 is, and then select an answer without ever adding the increase back to the original price. Needless to say, the test writers have prepared for this possibility. In this question, 75 cents, 25% of 3, would definitely appear in the answer choices. And if you've forgotten to add the original price of gas into your equation, you'd have selected it and gotten the wrong answer. So be careful and always check your work. Here's another question. An iPod that cost $200 in 2003 sold for 30% less on eBay in 2005. What was the price of the iPod in 2005? Here are your answer choices. A, $140. B, $60, C, $260, D, $170, and E, $230. This is probably a good place for a little tip. You've read the question twice, and you've moved on to the answer choices. You can actually eliminate some answers right off the bat by ballparking. That's just a fun way of saying estimating. Before we try this out, let's look at that question again. An iPod that cost $200 in 2003 sold for 30% less on eBay in 2005. What was the price of the iPod in 2005? From looking at the question, we know automatically that we're looking for a number that's less than 200. From our list of answers, we know we can eliminate every answer that's more than 200. So say goodbye to choice C, which is $260. And while we're at it, bid adieu to choice E, which is $230. Now, are there any other choices we can eliminate? What about choice B, $60? That's obviously way less than a 30% markdown on $200. So look at that. Without doing any math, we've already eliminated 3 answer choices, which gives us just 2 to pick from, and we owe it all to ballparking. This technique should be one of your best friends on the math section. If you can eliminate any answer choices that are out of the ballpark, you'll improve your odds of selecting the correct answer substantially. Before we move on, let's go on and answer our question. We know we're trying to figure out a price that's 30% less than $200, so we could just multiply 200 times 30%, which gives us 60. But we can't just leave it at that, of course. Subtract 60 from 200, resulting in 140. And guess what? Answer A is $140. So we've got our final answer. Excellent. Sometimes the GRE makes ballparking even easier by listing answer choices in ascending or descending order. So if you come upon answer choices written in ascending or descending order, start by looking at the middle choice. That's choice C, of course. If that answer choice doesn't work, then you can determine whether you need a smaller or larger number. Just by doing that, you can usually eliminate answers A and B or D and E, and then you'll find yourself in the familiar position of only having 2 answer choices to choose from. Talk about saving time and effort. Another type of percent increase-decrease question the GRE test writers adore are those that give you a first value and a second value, and then will ask you to determine the percent by which the value changed. So if the value increases, that's obviously a percent increase problem. And if the value decreases, you've definitely got a percent decrease problem. There are a couple of simple formulas for solving these kinds of problems. Take the difference between the 2 numbers and divide that by the smaller of the 2 numbers. Then, multiply the resulting number times 100%. Here's an example. In May, Joe paid $8 for a movie ticket. In August, the price of a ticket went up, and Joe paid $10 for a movie ticket. By what percent did the cost of a movie ticket increase? Using our formula, we first subtract 8 from 10. Then we divide the resulting 2 by our smaller number, which is 8. That gives us 2 over 8, which reduces to 1 over 4, or 0.25, 25%. Not bad. The formula for finding a percent decrease is almost exactly the same. This time, we're just dividing the difference between our 2 numbers by the larger one, which makes sense, right? Remember those 2 formulas. They'll save you lots of time. Proportions, ratios, and probability. This is one we like to do in tandem with percentages, just because the 2 subjects are so alike. Let's start with probability, which your math teachers taught you is equal to the outcome you're looking for divided by the total number of possible outcomes. If it's absolutely impossible for a given thing to occur, then the probability of it happening is 0. On the other hand, if something will definitely happen, it has a probability of 1 or 100%. Most of the time, though, probability is going to deal with the space between 1 and 0. In this case, probability will appear as a fraction, decimal, or percentage. Think about the classic coin flip example. If you want to flip a coin, you might wonder what the probability of it landing on tails is. If you're just flipping it once, the probability is 1 out of 2. We know that because probability equals the outcome we're seeking, tails, divided by the total number of possible outcomes, 2. The test will attempt to trick you by asking for the probability that the coin would land on tails on the 7th flip after you flip the coin 6 times. But it doesn't matter what happened in the previous flips. They don't affect the outcome of the 7th flip. Ditto for the 8th, 9th, and 10th. So the probability of landing on tails for the 7th flip is still 1 over 2. Beware, however, that you could get a question asking for the probability of landing on tails 7 times. You've already figured out that the probability of landing on tails once is 1 out of 2. So to figure out the probability of landing on tails 7 times, you just multiply 1 out of 2 times itself 7 times. Do that, and you'll end up with 1 out of 128. Sometimes people confuse probability with ratios. That's probably because we write odds, such as the odds of the Red Sox winning the World Series, as ratios. But with odds, we're really talking about probability. So what are ratios then? Ratios, you may remember, compare 2 parts. Even though they're written like fractions, they shouldn't be confused for fractions. After all, fractions describe the part of a whole. Ratios just compare one part to another. So if there are 3 girls in a class for every 4 boys, the ratio of girls to boys is 3 to 4. You might see that written as 3 over 4, or more likely as 3:4. The GRE will never ask you what the ratio of girls to boys is after telling you that there are 3 girls for every 4 boys. That's just way too easy. You're more likely to get a question like, for every group of 20 people Barbara invited to the party, only 7 showed up. What is the ratio of people who attended to people who didn't attend? The question tells you that 7 out of every 20 people attended the party. But it's not asking for the ratio of attendees to invitees. Instead, the question wants to know the ratio of attendees to non-attendees. So you first got to figure out how many people out of every 20 did not attend. That's easy. 13 out of every 20 folks didn't show up. So for every 7 people who did show up, 13 people did not attend. For these questions, it's important to read the question correctly and avoid flipping the ratio. Our question asked, what is the ratio of people who attended to people who didn't attend? Since we know 7 people attended, we should make sure 7 is the number on the left side of the ratio sign in our answer, and 13 is the number on the right. The incorrectly flipped ratio of 13 to 7 would more than likely be an answer choice in this case, so if you didn't read the question carefully, you might select it. Often, the test mixes things up with questions involving both ratios and percentages. You're likely to see a question like, Jim's mom made peanut butter and chocolate chip cookies. After Jim ate some of the cookies, there was a 4-to-1 ratio of peanut butter cookies to chocolate chip cookies. What percentage of the remaining cookies are peanut butter? To find the answer, we need to add the 2 parts, the numbers on each side of the ratio. Since we have a 4-to-1 ratio, we'll add 4 and 1, which gives us 5. Since that 5 represents the combined total cookies, we make 5 the denominator. Then, since we're looking for the percentage of peanut butter cookies, we stick 4 on top, which gives us 4 over 5. We should then be able to do the math in our head. Or better yet, just know that 4 over 5 is 0.8. Or 80%, so we'd say 80% of the cookies are peanut butter. For ratios on a much larger scale, we use proportions, which show that 2 ratios are equal. On the GRE, proportions involve some unknown number. It's your job to figure out the unknown. How about an example? If 10 boxes contain a total of 80 books, how many books would 6 boxes contain? To figure that out, we need to set up an equation. We know we've got one ratio of 10 boxes to 80 books. So on one side of the equal sign, we can write 10 over 80. We need to figure out how many books are in 6 boxes. So on the other side of the equal sign, we'll write 6 boxes over x. Now that we've set up our equation, we can solve for x. Use the bow tie method or cross multiplication or whatever you want to call it and multiply up diagonally from x to 10, which gives us 10x. Then, multiply up from 80 times 6, which gives us 480. This leaves us with 10x equals 480. Dividing both sides by 10 shows us that 6 boxes contain a total of 48 books. Distribution and the FOIL method. So far, you've lucked out. We've been showering you with word problems. You will see a lot of those, of course, but sometimes you'll hit what seems to be an endless trail of numbers and variables. Often, you'll see numbers or variables outside of parentheses, and inside the parentheses, you'll see numbers being added or multiplied. Yep, parenthetical expressions. We all remember what to do with those, don't we? Just in case, here's a refresher. Multiply each term inside the parentheses by the factor outside the parentheses. And there you have the rule of distribution, whereby you are to distribute the number outside the parentheses among all the terms inside the parentheses. Not the most original name, but hey, it was invented by mathematicians. What do you expect? Things get a bit more complicated when you have two parenthetical expressions side by side. We call that binomial expression. Here, we use the FOIL method, another leftover from high school math. Get it? Leftover? FOIL? Okay, never mind. FOIL is an acronym for first, outer, inner, last. And those words just happen to correspond to the 4 steps of multiplication we use when we've got to multiply 2 sets of parentheses. Let's do one, shall we? You may want to grab a piece of paper and a pencil for this one. We'll wait. Okay, write x plus 4 and put it in parentheses. Now, right next to the x plus 4, write x plus 2 and put that in parentheses. If the word binomial wasn't familiar before, it should be now. Now we want to change that binomial into the mighty polynomial. Hopefully your nomial memory is coming back. Yes, we know, nomial isn't a word. Bear with us. A polynomial, you'll remember, is an expression created from a bunch of variables and integers using addition or subtraction, or both. In the case of our binomial, we've got addition and nothing else. Let's get started. Since this very well could be criminally old material for you, we'll go slowly. First, multiply the first 2 terms together and then put them underneath or to the side or somewhere out of the way. X times x is x squared, in case you were wondering. Outer. Multiply the outer term of the first parenthetical expression, which is x, by the outer term of the second parenthetical expression, which is 2. So 2x. Write that down after your x squared. So as to not confuse this, we'll wait on the operators between the terms. Inner. Multiply the 2 inner terms together. In our case, 4 from the first expression, x from the second expression, 4x. Last. Multiply the 2 last terms together, 4 and 2, 8. Okay, if we'd thrown a subtraction operator somewhere in those parenthetical expressions, things would get a little more complicated. We took it easy on you. Put pluses between all those terms you just wrote down. Before doing any work, your polynomial should be x squared plus 2x plus 4x plus 8. 2x and 4x are like terms because they just have the plain vanilla x's on them, so you can add those together. Our final expanded polynomial then is x squared plus 6x plus 8. Ta-da! It would probably be a fine idea to practice doing that until you get good and fast at it. Factoring. Factoring sort of works as the opposite of what we just did. You might have heard of the FOIL method as a way by which you might expand binomials. By factoring, we can simplify complicated polynomials. When we factor an expression, we take the factor common to all terms in the original expression and yank them out. We don't throw them out altogether, we set them outside the expression beside some good-looking parentheses and end up with a new factored version of the same expression. So, say we're adding AB plus AC. These 2 arbitrary terms have the letter A in common. Put B plus C inside some parentheses and stick A outside the parentheses. This way, if we wanted to expand it all out, we could multiply A by everything inside, as per the rule of distribution. You can save some time on factoring by memorizing 3 common factored forms called quadratic equations. Yeah, we've heard that term before, haven't we? Quadratics are expressions with 2 variables, both of which are squared. Let's look at one. Now would be a good time to grab that pencil and paper again, in case you put it down. Put x plus y in parentheses and sidle it up next to x minus y in parentheses. No matter what, that expands out to x squared minus y squared. Always. There might be numbers involved, there might be different letters, but it doesn't matter. The expanded form of those binomials is always the same. So if you remember that x plus y times x minus y is always x squared minus y squared, you won't have to waste any time doing any FOIL expanding. The second quadratic expression to remember is x squared plus 2xy plus y squared. This is probably the first quadratic equation you learned. In its factored form, x squared plus 2xy plus y squared appears as x plus y squared. The squared sign is outside the parentheses, reminding us that we're multiplying 2 sets of identical parenthetical expressions together. The last quadratic equation to remember is x squared minus 2xy plus y squared. In its factored form, x squared minus 2xy plus y squared is x minus y squared. Hopefully, you wrote all that stuff down for practice later. Data interpretation. Earlier, we mentioned the math section of the GRE includes 3 to 5 data analysis questions. These questions provide you with data using bar graphs, pie charts, and line graphs. Typically, data analysis questions require you to work with some combination of percents, fractions, or decimals. As with any other non-quantitative comparison question, always look at the answer choices before solving the problem. That way, you'll know what format your answer should appear in beforehand. Of course, we can't show you any charts, graphs, or tables here. It's an audiobook. What we can do, however, is share the wording of a couple sample questions. Listen to them closely so you have a good idea of what types of questions you might be asked. You might, for instance, be shown a couple of pie charts comparing the preferred leisure activities in 1985 and those in 1998. The accompanying question might say, to the nearest 1%, what percentage decrease in popularity occurred for snorkeling between 1985 and 1998? You know what that sounds like? A percentage decrease question. So you'd work it just like the percentage decrease problem like we did earlier. Here's another question. Based on the same 2 charts, which of the following activities declined in popularity by more than 10% between 1985 and 1998? Even without looking at the chart, you probably know how to solve this one. Just look at the 2 charts and see which activity took up a considerably smaller piece of the pie in the second chart than in the first one. Believe it or not, a lot of data interpretation questions really just require you to use your eyes to track down information and answer the question. One more. In 1998, if 15.13% of the other category is skydiving and 2,348 people surveyed prefer skydiving, then how many people were surveyed total? Sounds like a proportions question involving percentages. And, since you're not skipping around the audiobook, we're going to trust you already know what to do here. Before we move on, though, a quick comment on the question we just introduced. You might be asking yourself, 15.13%, 2,305 people? Who has time to work with such monstrous numbers? This is a pretty typical response to GRE data interpretation questions. Thankfully, you don't have to take that stuff literally. Data interpretation questions with messy numbers will usually include the word approximately or to the nearest 1%. This is a not-so-subtle hint that you should be ballparking. So if you get a chart question that asks you to find 8.43% of 17.53, you can and should ballpark your answer by rounding 8.43 down to 8 and rounding 17.53 up to 18. Sometimes GRE data interpretation questions ask you to deduce something from a graph or chart rather than perform hard math. These questions are usually phrased as, which of the following statements can be deduced from the chart? Then you'll get to choose from a series of statements. For these questions, the GRE writers sometimes throw in more information than you'll need, which is a way to test your ability to figure out what information matters in a set. Other times, they'll mention important information only in the fine print below the chart. They might even stick key information in the graph title, assuming you won't bother to read or absorb the title. Thankfully, there's an easy way to avoid falling into these traps. Read everything closely, and remember that a number that appears in a chart isn't always necessary to solve the problem. Geometry. We've talked about numbers and letters. We've talked about charts and graphs. It's probably about time to talk about shapes. That's not to say GRE geometry is superbly difficult. Most geometry problems on the GRE are essentially algebra or arithmetic problems accompanied by an illustration. As with the data interpretation stuff, the trick is knowing how to read the data. So if you understand the geometry concepts we're about to review, you should be able to do just that. Of course, since we can't actually show you graphs, circles, triangles, or anything else that needs a visual representation, you're going to have to spend some quality time reviewing geometry outside of this audiobook. Before you do that, though, we'll share some tips for tackling GRE geometry problems and review the geometry vocabulary and concepts that you'll encounter on the GRE. You already know to read every question twice and review the answer choices before trying to solve the problem. Let's add one more strategy to your tool belt. Drawing. Surprisingly enough, some GRE geometry questions won't give you whatever circle or angle or triangle you need to answer the question. Or maybe the illustration they will give you won't have everything you need on it. So if there's a reference to a diagonal line in the question, for example, there's a good chance you won't see a diagonal in the accompanying illustration. There's a decent enough reason for this. If they provide the full and complete drawing, the answer would be too obvious. You shouldn't be guessing, of course. As we mentioned earlier, the test center will give you some scratch paper. You can and should use this paper to draw out figures. If drawing helps you visualize the figure, go for it. If the illustration on your computer doesn't make sense, ditto. Drawing out the diagrams, figures, and even graphs can save you a lot of time and sanity. Coordinate geometry. As you probably remember from high school math, the coordinate plane, that graph of grid lines we use in geometry, has two intersecting axes. The horizontal one is the x-axis. The vertical one is the y-axis. The intersection of the x and y axes creates 4 quadrants. Every point on the plane is located in one of these 4 quadrants. The one exception is the origin, which is, obviously, where the x and y axis intersect. Every point is made up of 2 numbers, identifying said point's location on each axis. The first coordinate is the x-coordinate, and the second is the y. Positive x-coordinates are left of the origin, and positive y-coordinates are above the origin. Negatives are right and down, respectively. And usually, coordinates appear inside parentheses. Sometimes, the GRE will ask you to determine the distance between 2 coordinates. Thankfully, there's a handy formula for this. To find the distance between 2 sets of coordinates, start by subtracting the first x-coordinate from the second x-coordinate and squaring the difference. Then, subtract the first y-coordinate from the second y-coordinate and square the difference. Afterwards, add the 2 squared numbers together and take the square root. Ta-da! You've got the distance between 2 points. How about an example? Let's find the distance between the coordinate 7, 2, and the coordinate 3, 5. 7 minus 3 is 4. Square 4, and we get 16. File that away. 2 minus 5 is negative 3, which, when squared, is 9. Positive 9. Why? That's right, because a negative times a negative is a positive. Good. So now we add 16 to 9, getting 25, the square root of which is 5. So the distance between our 2 points is 5. Next, slope. Slope is essentially a measure of the grade or steepness of a straight line. The math is relatively easy and asks you to find the vertical difference in 2 points on the line and divide it by the horizontal difference in the same 2 points. An easier way to remember this is rise over run. Starting to come back a little bit now, isn't it? Do you remember the letter used to signify slope? Just in case, it's a little lowercase m. Okay, enough words. The formula for m is y2 minus y1 all over x2 minus x1. A word of caution, quickly, before we do a practice problem. Sometimes the GRE will sub the m for an a. Why? No idea. It just happens. Don't be thrown by it. Here are a couple of important things to know about slope. First, parallel lines always have the same slope. So if line AB has a slope of m, any line parallel to it also has a slope of m. Perpendicular lines are another story. Anytime you've got 2 perpendicular lines, their slopes will be opposite reciprocals of each other. As we mentioned earlier, you find the reciprocal of any number simply by plopping a 1 on top of it. So the reciprocal of m is just 1 over m. If m happens to be a fraction, any idea what you might do? You flip it over. Slope is pretty important because you'll likely get questions asking you to create an equation that describes some line passing through a couple of points. And slope is integral to figuring out what that equation is. Thankfully, there's a little equation form you can fill out that does most of the work for you. Y minus y1 equals m times the parenthetical expression of x minus x1. Write that down. So what's with this x and x1 business? It's actually so much easier than you'd think. x1 is the x-coordinate for one of your points. y1 is the y-coordinate for that same point. Easy, right? For the point-slope equation, you'll use just one of the points that you're given. You won't plug in anything for x or y, so the variables x and y will appear in your answer. For this type of problem, you'll be asked, what is the equation of the line passing through? And you'll be given 2 points on the line. Before you can get that equation, of course, you'll have to run your 2 points through the slope equation so that you can have m. Once we figured out the slope, we can plug it in for m in our equation, y minus y1 equals m times x minus x1. Then, all we have to do is plug in the coordinates of one of our 2 points. When working this type of problem, your final answer should have the x and y on the same side. So, for instance, if you came up with negative 2x plus 5y equals 18, that would be an appropriate point-slope equation. Assuming you did the math properly, of course. Now that we know how to find the point-slope equation, we should discuss the equation for lines that cross the x or y axis. When the line intersects with one of the axes this way, we call it intercept. So the point where a line crosses over the x-axis is the x-intercept. Because that point intersects with the x-axis, that particular point doesn't go up or down at all. So all x-intercepts have a y-coordinate of 0. Likewise, the point where a line crosses the y-axis is the y-intercept. Because that point doesn't go left or right on the x-axis, it always has an x-coordinate of 0. So think opposites. The x-intercept has a y-coordinate of 0, and the y-intercept has an x-coordinate of 0. If a line has an x or y-intercept, you'll need a special formula to find the equation of the line. The formula we use is called the slope-intercept equation. How will you know you need to use this formula instead of the point-slope equation? The question will either tell you the intercept, or it will give you the intercept and ask you to find the equation of the line. The slope-intercept equation is pretty straightforward. It's y equals the mx plus b, where b is the y-intercept. B is always, always, always the value of the y-intercept. It is never the value of the x-intercept. Just like the point-slope equation, the x and y here are variables. You don't need to substitute anything for them. They should show up in your answer. M, of course, is the slope. So, say you've got a slope of 3 and a y-intercept of negative 2. You'd write your slope-intercept equation as y equals 3x plus negative 2. Or, for simplification's sake, y equals 3x minus 2. That wasn't so bad, was it? If you can memorize the formulas and read a graph, you should be fine. Just be sure to practice reading and working with coordinate planes. That way, nothing should rattle you on the big day. Lines and angles. So, we've been talking a lot about lines, and for good reason. You'll notice, of course, that they just happen to be everywhere. And much of the time, they're completely flat or completely vertical when we see them. You can expect to see some lines like that on the GRE, either by themselves or as parts of other shapes. And when you see these lines, it's important to know that all lines are also angles. To be more precise, all lines are 180-degree angles because they are perfectly flat. Of course, when they connect to form those shapes, they create angles, which we'll talk about more in just a minute. Before we do that, though, let's talk about lines that never intersect. Parallel lines. This is a popular GRE diagram. Two parallel lines bisected, that means cut in half, by another line on an angle. Can you picture that? Note that you now have 6 different sections. You might be tempted to call that 6 new angles, but you'd be wrong. You actually only have 2 new angles. That's because 3 of those angles are exactly the same, and the other 3 are also exactly the same. The large ones we've created, the obtuse angles, will all be more than 90 degrees. The small ones, which we call acute angles, all come in under 90 degrees. That is an extremely important concept, so memorize it. Any diagram with 2 parallel lines intersected by another will create only 2 different angles. Sometimes the GRE will give you questions with one of these diagrams where some of the angles are given in degrees and some are expressed as variables. It'll then be your job to figure out what the variables are. This should be pretty easy. Big angles are the same, small angles are the same. You can figure one out from the other by taking it and subtracting it from 180. Obtuse and acute angles aren't the only angles you'll see on the GRE. You'll also see plenty of 90-degree angles, which are formed when one straight line is perpendicular to another straight line. You'll know you've got a 90-degree angle on your hands when you see a little box at the intersection of the angle's sides. And this brings us to the union of lines and angles. Shapes. On the GRE, the shapes you're most likely to see are triangles and quadrilaterals. And, as we'll discuss a little later, circles. By the way, here's an interesting bit of useless trivia. While it may appear as though circles are not made up of lines and angles, that's just not true. Circles are actually made up of a number of lines approaching infinity and a number of angles approaching infinity. Actually, there's a special line called a line at infinity in topology, which can only be represented by a circle. When it comes to shapes on the GRE, you'll be tested over three primary things: angles, area, and perimeter. Area, of course, is the amount of space inside a figure. As we go over different shapes, we'll review the formulas for finding the area of each of these figures. Perimeter, on the other hand, is the distance around the outside of a figure. It is the lines you see when you draw the shape. To find the perimeter of any figure with sides, you just add up all of the sides of the figure. Quadrilaterals. We'll start with our four-sided friends: rectangles, squares, parallelograms, and trapezoids. All quadrilaterals have four angles, which have a total of 360 degrees between them. We repeat, all the angles of any quadrilateral add up to 360 degrees. So if you're working with a quadrilateral where your angles aren't adding up to 360 degrees, you're doing something wrong. In a rectangle, as you probably remember, the opposite sides are parallel and each of the four angles measure 90 degrees. This means opposite sides of a rectangle are also the same length. Perpendicular sides might have different lengths. They don't have to have different lengths though. Some rectangles are also squares. Let's say you want to figure out the area of the rectangle. You just multiply the length of the rectangle times its width. In other words, multiply the length of one side times the length of the other side perpendicular to it. Here's your rectangle area mantra. Area equals length times width. Finding the perimeter of a rectangle is equally easy. Since a rectangle's parallel sides have the same measurement, you can find the perimeter of a rectangle by doubling the length and width and then adding those two products together. So how about when all sides are measured the same? The square is even easier to work with since all of its sides are equal. The area of a square is one side squared. The square where each side measures 4 inches would have an area of 16 square inches. Calculating a square's perimeter is just as easy. Multiply a side's length by 4. Okay, let's move on from the easy stuff. Let's look at a quadrilateral that tosses our neat, equal angles out the window. The parallelogram. As the name implies, you can think of a parallelogram as a shape created by the intersection of two sets of parallel lines. Perimeter calculations don't change, of course. But with parallelograms, it's doubtful you'll be working with perimeter. You'll be figuring angles. Thankfully, this is pretty easy too. In a parallelogram, opposite angles are equal, as are opposite sides. This means the big angle and the small angle in a parallelogram add up to 180 degrees. And just like the angles created by the parallel lines we talked about earlier, the vertical angles are equal in a parallelogram. In case you've already forgotten, the vertical angles are the angles that are directly across from each other. All rectangles and squares are parallelograms, but all parallelograms aren't squares and rectangles. It all depends on those angle measurements. If your parallelogram isn't a square or a rectangle, finding the area will be a little trickier, but not much. The height of the shape won't be one of those angled parallelogram sides. Instead, you'll have to mentally draw a line from the apex of one angle straight to the bottom, sort of making a triangle. Measure that, and you can multiply it by the width of the shape and get an area measurement. Another pretty common diagram on the GRE is a parallelogram bisected by a diagonal line, creating a couple of triangles. When you have one of these, triangle know-how is being tested, disguised as a quadrilaterals question. Sneaky, huh? In a few minutes, we'll review some key triangle formulas and facts. Commit these to memory, and you should be A-OK, whether you see a standalone triangle or a triangle made with the help of a quadrilateral. Anytime you see a square or a rectangle with a diagonal line, the angles created by the split will measure 45 degrees. This means you'll be working with a 45-45-90 triangle. You'll want to know that in a 45-45-90 triangle, the two sides across from the 45-degree angles are each the same length. The side across from the 90-degree angle is the longest. Often, when you see a quadrilateral with a diagonal through it, you'll be given the length of just one side of the quadrilateral and the length of the diagonal. Then, the question will ask you to calculate the measurement of the remaining unknown side. This is another example of a triangle question disguised as a quadrilateral one. Here, you have to break out your Pythagorean theorem. As you probably remember, that's the formula for calculating one side of a triangle. And, since we're talking about a parallelogram cut into a triangle, it comes in handy here. The Pythagorean theorem is a squared plus b squared equals c squared. A and B are two sides of the triangle, and C is the longest side of the triangle, usually referred to as the hypotenuse. The hypotenuse is the line opposite the right angle. You can use the Pythagorean theorem to find any of the lines of the triangle, not just a hypotenuse. Let's do one. Say we've got a hypotenuse of 5 and a known side of 3. We need to find the length of the other side. We'll call the known side A. The hypotenuse, of course, is C. We can rewrite the equation as 3 squared plus b squared equals 5 squared. Do a little simplification. 3 squared is 9, b squared remains the same, and 5 squared is 25. Our equation now becomes 9 plus b squared equals 25. Like any other equation, get all the numbers on one side and isolate the variable. The result? B squared is equal to 16. To find b, we just take the square root of both sides. Now, b equals 4. Easy. We told you, GRE geometry problems are just illustrated algebra and arithmetic problems, didn't we? There's one more quadrilateral that appears on the GRE, trapezoids. Unfortunately, they're not quite as easy to work with as squares, rectangles, and parallelograms. Only 2 of their 4 sides are parallel, and none of their sides are the same length. A trapezoid's parallel sides are called bases. More often than not, you'll find the trapezoid drawn with a dotted line inside, perpendicular to the bases. The 90-degree angle that results is used for reference to find the diagonal side across from it. This, by the way, happens to be 2 things: the hypotenuse of that right triangle and one side of the trapezoid, which means trapezoids have 2 90-degree angles. You'll also notice that the 2 angles attached to the longest base of the trapezoid are acute. The other 2 angles are obtuse. No matter what, of course, the 4 angles of the trapezoid will always equal 360 degrees. Just like the parallelogram, the height of a trapezoid is a perpendicular line drawn from the corner of the top base to the bottom base. It's not one of the sides. Often, you'll have to use your knowledge of 90-degree triangles to figure out the height or the length of a side. Before we leave trapezoids for triangles, you'll need the equation for figuring out the area of a trapezoid. It's a little more complicated than our previous 4-sided shapes. The area is equal to the height of the trapezoid, that perpendicular line drawn from the top to the bottom of the shape, multiplied by the sum of the bases divided by 2. Confused? Okay, let's do it one more time. The area of a trapezoid is equal to its height multiplied by 1/2 of the sum of its bases. If we call the bases A and B, the height line H and the area A, an equation of the area of a trapezoid might look something like this. A equals H times AB over 2. Let's try an example. You've got a trapezoid where one base is 3, the other base is 6, and the height is 5. 3 plus 6 is 9, divided by 2 is 4.5. Multiply 4.5 times 5, the height. The area then is 22.5. Before we head into triangles, a quick word about measurements. If you get a problem looking for the area and they give you a unit measurement like inches, as opposed to a measurement with just a number with no accompanying unit, please remember that the result will be in inches squared. We guarantee you There'll be at least one problem where two exact numbers are given, and only one is notated properly. Area is inches, feet, yards, meter, whatever, squared.